state. Based on this important information, we can define a greedy algorithm based on the combination of backward cost and forward cost. As you remember, the backward cost is a real cost that can be calculated from a starting state to get any node. It is calculated, not estimated. That means Gn is the summation of the cost of some links in the path between a source node to target node, or any node to target node. And for forward cost, we have just estimation. It cannot be calculated in reality because the goal is far from our location. Because of that, Hn is just a heuristic or estimation from the distance of a pair of nodes. Hn and Gn is combined together to define Fn, and the greedy algorithm focus on Fn for choosing the next state. For example, we start from S. All of the heuristics are given before starting. For any node, we define an object, and in the object, the value of G, H, and F can be saved. For a starting node, G is 0 because there is no movement, and the heuristic is copy-paste, 6. 6 plus 0 is 6. The value is 6 because there is a single option between S and A. We move to A, but when we enter to A, the information of the corresponding object should be updated. For updating G, we use addition of the cost between the predecessor node and A, that is S. The value of G in S is 0, plus the value of the cost connected between S and A, 1. G is updated 1, and heuristic copy and paste. Now for A, we have 3 options: moving to B, moving to D, or moving to E. For all of the objects with respect to B, D, and E, we need to update the information. Again, the value of G is defined with respect to the corresponding cost between the predecessor and their node, and the predecessor cost is 1 is added to the cost of link. In this example, the cost of A is 1 plus the cost for A to B. A to B is again 1. G is updated 2, and the heuristic is copy. Similar process will be happened on D and E. Now, the grid algorithm chooses the least F. F for B is 8, F for D is 6, and F for E is 10. D is the best. We continue the process from D. D has a single neighbor. The neighbor is G. For the object corresponding to G, we update G and H. H is copy and paste, and G is the addition of 2 plus 4. 2 plus 4 is 6. And because this F value is less than the F value of B and E, we stop. If the value of B and E is less than a value of G, we continue. For example, in this simple network, we start from S. It has 2 neighbors. For neighbor A, the G, H, and F is 2 to 4. And for B, the cost of G is 2, the heuristic is 1, and its summation is 3. 3 is better to continue. We focus on B. B has a single neighbor, G. We define the value of G, H, and F for G. They are 5, 0, and 5 because other node with F1, F equal to 4 for A, and 4 is less than 5, we need to continue. And the algorithm should process the neighbors of A. The neighbors of A is G, and now G is 4, H is 0, and F is 4. The node with the least F is chosen as the optimal solution. S, A, and G is optimal solution whose G and H are equal because H is 0. This is optimal solution. The other solution, SB to G, is not optimal. In our class, we named it as the suboptimal. Please pay attention. Suboptimal solution is a solution whose cost is greater than the optimal solution. For optimal solution and for suboptimal solution, as you see, the value of G and value of H are equal because the optimal and suboptimal solution receive 2 goal, and for the goal, its value is 0. Thus, remember, for optimal solution and suboptimal solution, F value and G value are equal, but both of the F and G for suboptimal is greater than the corresponding components of the optimal solution. But in previous lecture, we have a bad example where we started from S, and for the neighbors A and G, we calculated value of G, H, and F. For S, the value is 0, 7, and 7. For S2A, we have the G equal to 1, and the heuristic is 6. 1 plus 6 is 7. Again, for this next neighbor, S2G, we define the G value equal to 5 and H value equal to 0. 5 plus 0 is 5. Thus, algorithm terminates because there is no other option whose f is less than 5. In the previous example, as you see, when we receive to 5, we have another option, S to A, whose cost is 4, that is less than 5. And so we continue the expansion of A and found the optimal solution. But in this example, 7 is greater than 5, thus expansion of A is not needed, and the algorithm terminates. But the solution is not optimal because, as you see, the optimal solution is S to A to G with cost 4. But our algorithm, our greedy algorithm, cannot find the solution. What's the matter? The solution is related to the definition of heuristic. As you remember, for any problem, it is possible to define the different kinds of heuristics. But for all of the heuristics, we cannot guarantee to find optimal solution. We need to limit our attention to admissible heuristics. Admissible heuristics is very, very important concept for research. For research, we can show that when we use admissible heuristic, we have a guarantee to find optimal solution in the least time. What is admissibility? For any problem, we can follow attitude, pessimistic or optimistic attitudes. When we look at a problem with pessimistic attitude, we consider the worst cases. But when I try to solve a problem with optimistic heuristic, we focus on the simplified version of the problem. This is the meaning of heuristic, admissible heuristic. Admissible heuristic is is an optimistic estimation for destination between any node and the goal. And this simplified problem can be used to determine the optimistic heuristic for any searching problem. If you are interested to define admissible heuristic by mathematical equation, please note that a heuristic can be defined for all of the nodes or all of the states by considering a positive value, positive or zero. That means that the heuristic or estimations cannot be defined as negative value, but zero value is acceptable. But since Hn or admissible heuristic should be defined in optimistic manner, the value of H should be less than the optimal solution. That means if the optimal cost of the path between the node N and the goal is H star N, then the heuristic of the corresponding node belongs to the interval of 0 up to H star N. It is a good question that H star N as the optimal cost cannot be accessible from the node, because if you find the optimal cost to travel to the goal, the problem is terminated and we do not need to expand more nodes. In the reality, when we are inside of a state, we just access to the backward cost, because backward cost is calculated as the summation of the cost from the starting node to the current node. But for the distance between the current node and the target node, we have not any sense. We have just some estimation. Because of that, in this definition, instead of focusing on the H star as the optimal solution, we say that the property and characteristics of optimal solution is better to follow. To explain more, consider this agent. This agent, for movement to the goal state, needs to come back until the end of the barrier, and then it can go down and move right or move left, and again move down, and again move left, and again move down, and continuing a straight line to access to the goal. This crowded and complex path is defined based on the constraint the agent cannot fly to receive to the goal. In the right shape, when you use Euclidean distance, you ignore from some constraint and say that the agent can go on a straight line or fly on a straight line. Because you ignore from some constraint, a simpler solution can be accessed. And you can find the estimation of distance between the current node and the goal node with Euclidean distance. In the left shape, in reality, the agent cannot cross the barrier. The obstacle and barrier are very, very hard. But in the simplified problem, we can assume that the agent can fly over obstacle or fly a direct path between the origin and the destination. When the agent can enter in the obstacle, the value of the cost decreases, because in the admissible heuristic you need a cost less than the optimal solution. By usage of both of this definition of the distance, you can define some estimation for Hn with different values. A trivial heuristic is 0, because 0 can be used for all the problem. But as you remember, come back. When you ignore from heuristic or you set h equal to 0, your greedy algorithm focus on fn equal to gn. When your focus is gn, your algorithm is uniform cost search. Uniform cost search again can find optimal solution, but the processing time are great. Because of that, instead of uniform cost search with heuristic equal to 0, it is better to define some heuristic close to h star n. As much as hn is closer to h star n, your heuristic improves and the processing time decreases. Now, come back to previous example. As you see, the exact cost between A and G is 3. Because of that, when we need to define admissible heuristic, the heuristic of A is at most 3. That means HA can be defined 0, 1, 2, or 3. But heuristic of H cannot be admissible if you use 4, 5, or 6 for the heuristic. Because of that, when we face such inadmissible heuristic, we say that we have not guaranteed to find optimal solution, as you see in this example. Again, for S, the exact cost is 4. When the exact cost is 4, in the admissible heuristic, you need to define the heuristic of S less than or equal to optimal solution. That means you can define h of S equal to 0, equal to 1, equal to 2, equal to 3, or equal to 4. The value greater than 4 is not useful for A star algorithm. And as you see, h equal to 7 shows that the heuristic is inadmissible, and we have not guaranteed to find optimal solution. But in the previous example, the exact cost between A and G is 2, and the heuristic is 2. 2 is less than 2, thus heuristic of A is admissible. Again for B, the exact cost between B and G is 3. Heuristic is 1. 1 is strictly less than 3. Thus, again, the heuristic of B is admissible. And for S, the exact cost between S and G is 4. The heuristic is 3. 3 is strictly less than 4. Thus, the heuristic is admissible. When the heuristic is admissible, as you see in this example, the ASR can find optimal solution, but when the heuristic is not admissible, ASR cannot find optimal solution. This is the meaning of admissible heuristic. Do you have any question about admissibility? No problem? No question? I continue. When you have a question, please ask me in that place. Now, we need to discuss about the guarantee of ASR to find optimal solution. Just we focus on research in this lecture. In research, we have such basically searching environment that is shaped by different nodes in the different level of the tree. We define some fringe based on our strategy. In this example, it is our fringe. As you see in the fringe, we search some nodes to find the optimal solution. But before entering in the mathematical analysis, we need to define some assumption. The first assumption is that A is optimal goal node. That means the cost of A, GA, is equal to the FA, and both of them are the least among all of the nodes in the tree. The second assumption, B is suboptimal goal No. As you remember in previous example, sorry, before. Uh-huh. Uh, in this example, SAG is optimal solution, and the cost of this pass is Gn equal 4, Fn equal 4. Both of them are equal. And the suboptimal is SB to G. SB to G, again, access to goal. Because of that, it is optimal, but because the cost is greater than the optimal cost, we entitled it as the suboptimal. Again, for suboptimal, Gn and Fn are equal, but both of Gn and Fn are greater than the corresponding values of optimal solution. We come back. When I say B is suboptimal goal node, the cost of G and the cost of F are greater than the cost of G and F for optimal solution, that is A. And also assume that H is admissible. It is a necessary condition. Without admissible heuristic, we cannot derive the necessary result of guarantee. Now, we have some way to prove the result. We consider a violation example. In this violation example, we say that A and B are considered in the tree search, but if A will exist from the fringe before B, that means the optimal solution can be found before any suboptimal solution. That means we rapidly can find the optimal solution. But if A is not inside of the fringe, we cannot guarantee to find optimal solution in the least iteration times. Now we show that this condition does not happen. For proving this assertion, consider B is on the fringe and A is outside of the brain. If A is inside of the fringe, because the F value of A is less than the F value of B, the greedy algorithm select A before B, and thus the optimal solution obtained and the algorithm terminates. Otherwise, if A is not in the fringe, we have a pass between the a starting node and A because our tree is connected. When you face with connected tree, all of the nodes are accessed by root. Because of that, we have a root in the tree starting from the starting state, containing some links to receive A. Maybe there are a lot of links in this path, but one of the nodes in this path is on the barrier of the fringe. That means when we started from starting state and expand different nodes, we can check all of the neighbors, and one of the neighbors in the barrier of the fringe can be denoted as N, who is the bridge between the starting node and A. This is the bridge on the path. Now, we analyze something about the different behavior between N, A, and B. The first one, we claim that N be expanded before B. To show this one, we consider the relationship between Fn and Fa. As you remember, because A is goal, and in the goal H is 0, Fa and Ga are equal. Now, H is admissible. Because of admissibility of H, the value of Ga is greater than or equal to Fn, because in the Fn you have two parts, Gn and Hn. Gn is a forward cost, that is some forward cost between the starting node and node N, plus a positive value or zero value denoted with Hn, and based on the definition of Fn, both of Hn and Gn are positive. That means that Fn is summation of Gn and Hn, and when Fn is less than Ga, you can substitute the Ga with Fa, and when Fn is less than Fa and your algorithm is greedy, it tries to expand N before A. Thus, we say that Fn is less than Fa and the greedy algorithm checks the Fn before Fa and expand all of the nodes of n. Expand all of the nodes of n. For the next step, we say that Fa should be less than Fb. Why it is true? We say that B is suboptimal because in the suboptimal and A is optimal solution, for both of F and G, we have the corresponding G and F of A is less than the corresponding value of G and F for suboptimal solution. Because of that, again, Fa is less than Fb. Now, please pay attention. N expounded before B and Fa is less than Fb. If we combine these results, we receive that N expounded before B and all of the nodes in the neighbor of N is expanded before B, and because one of the predecessor of A expand before, we have to check the value of F, and because again Fa is less than Fb, in the previous step we should check the optimality of Fa and terminate before receiving to B. This shows that A star in the least time can find the optimal solution A before any suboptimal solution. It is enough to say that A star is optimal and with the least computation time can find the optimal solution. When you improve the quality of heuristic, A star can find the solution in less time. As much as quality of heuristic improves, A star can find solution sooner. That's enough. Do you have any problem? Do you have any question about what happened in this proof? Are you happy with all of the things? Maybe all of the topics are clear. Not important. We need to compare the quality of two different algorithms, uniform cost and A star. As you remember, in the uniform cost, when you enter in one state, you uniformly evaluate its neighbor because you check all of the neighbors in uniform manner. The fringe is similar to BFS fringe. that is layered by layer, check the costs of nodes. But in ASA, you have some estimation about the distance between any node and the target node. Because of that, your friend is smaller than the corresponding friend of the uniform class search. As much as you improve the quality of heuristic, the friend of A star would be thinner. This is the difference between uniform class and A star. Another visualization. When you implement uniform class search, you start from a single node. You uniformly consider all of the nodes in the neighbors of the current node. Again, you choose one of the neighbors and again define uniformly all of the neighbors of neighbor. Again, between all of them, you search all directions. Because of that, the friend of uniform class search is similar to a circle. But when you implement a star, you started from some node. This node is connected to many neighbors, but each of the neighbor has an estimation to guide your search to goal. When you choose some smaller fn between all of the neighbors, you focus on the most important parts. Again, you consider a thinner range compared to the uniform class search. There are some video for yourself. Please check it. Now, we compare three kinds of the algorithm. The first one is greedy. The second is uniform class. And the third is ASR. As you see, the fringe that is searched by greedy algorithm is the least among algorithms. But what is the drawback of the greedy algorithm? What's the drawback? Do you have any idea about the drawback of greedy algorithm? No one? No response? What's the matter? Why are you silent? Because greedy algorithm cannot guarantee to find optimal solution. This means although the range of the greedy algorithm is limited, but it can find some suboptimal solution without any guarantee to find optimal solution. This drawback limits our attention to use greedy algorithm for all of the problems. As a summarization, greedy algorithm is one of the best options, but without guarantee. It is a good option because the processing time of greedy algorithm is usually small. But why we don't use greedy algorithm for all of the tasks? Because it cannot guarantee to find optimal solution. Now, focus on uniform cost and ASR. As you see, in the uniform cost and ASR, we can find optimal solution with different steps. Both of them are optimal, but uniform cost search the neighbors in uniform manner. That means all of the neighbors of uniform cost can be checked by uniform cost algorithm. But ASR considers the heuristic values. Heuristic values leads ASR to check a subset of the states compared to the uniform cost. That means that ASR has guarantee to find optimal solution, and the searching space for ASR and its range is thinner than the corresponding sets in the uniform cost. Thus, if you prefer to find a solution without guarantee to optimality, greedy algorithm is good. If in your task the quality of solution is important and you need to guarantee to find optimal solution, I prefer to use ASR. If you have not any information to define the heuristic greater than the trivial heuristic. In these cases, the unique proposal is usage of uniform cost that assumes h is equal to 0 and search a great fringe to find the optimal solution. Again, I am ready to respond to your question. Is there any question? No one? All of these things are okay? It's okay. Thank you. Now, the last part of our lecture in this class is how to create heuristic. Creating heuristic, as you see, is the most challenging problem in the ASR implementation. For defining the good heuristic, we remember that the small heuristic is not good because, for example, h equal to 0 leads a star to uniform cost search. But when you try to increase the amount of heuristic, you can guarantee to decrease the number of states that should be searched or expanded by a star algorithm. To follow this aim, usually we define some relaxed problem. What's the meaning of the relaxed problem? Please pay attention to previous example. For example, this agent should meet different constraints. For example, this agent cannot cross the barrier, cannot fly over the obstacle. These constraints are hard for finding optimal solution. But we can ignore from this constraint and, for example, say that I enter in the barrier and receive to the goal. When you define a new problem whose constraints are less than the original problem, you receive a relaxed problem. In the relaxed problem, sometimes you ignore from all of the constraints, or sometimes consider a subset of constraints. Both of them leads you to relaxed problems. Consider another example. In the road network, you cannot fly over a straight line to travel between a pair of nodes. And the roads are not straightforward, are not a straight line. In many problems, you should select some longer path to to travel between different nodes. But if you ignore some constraint and say that I can fly, if you can fly, the straight line between any nodes can be defined as the heuristic. Thus, for any given task, if we can ignore from some constraint, we obtain some relaxed problems, and in these relaxed problems, we can find simpler solution. With respect to simpler solution, we can define admissible heuristic. When we define admissible heuristics, we can use a star with considering a value as a summation of G and H, and we can solve the problem very, very efficiently. Thus, we can define different admissible heuristic by ignoring from different subsets of constraints, and based on the different constraints, we can find the best heuristic. Which is the best heuristic? When you consider all of the constraints. When the heuristic is weaker, when you consider a relaxed problem with less with less constraints. Are you okay with this definition? Are you okay with this definition of relaxed problem? Do you have any ambiguity in relaxed problem? No one? No response? Okay, I continue. Consider another example. It is one of the famous example of heuristic. Please pay attention to this example completely. In 8 puzzle, you have different tiles with different numbers, and you should to sort them to a go state. In the reality, the tiles are locked together. When the tiles are locked together, you cannot detach them. But in a simplified problem, you can detach the tiles and change their location in the puzzle. For this situation, you move the tiles simpler. For example, 7 is in the corner of start state. But the location, the best location for 7 is there. Thus, we are a miss location for 7. Again, for 2, we have the same problem. And for the next, and for the next. By enumerating the necessary replacement of tiles, we can define a heuristic. But it is the solution of a simplified problem because I cannot change the location of 7 by detaching the tiles, and they are locked together. If you use such heuristic, for example, for this starting state, you can enumerate the mislocated tiles. They are 8. This means all of the tiles are located wrongly. For other state, you can do the same process. Now, consider the different algorithm, uniform cross search, and this heuristic inside of A star. As you see in this table with different steps, we compare the average of expanded node for uniform cross and for A star with respect to this heuristic. As you see, the number of expanded nodes for step is 112, and for 8th step is 6,300, and it increases exponentially for more steps. For example, for 12 steps, 3.6 cross 10 power 6 nodes should be expanded. This is very, very great. But if you use the heuristic algorithm, by ASR with this simple heuristic, for first step, you consider just 13 expanded node. And for 8 steps, at 39 expanded node should be considered. And for 12 step, 227 expanded nodes should be considered. That is very, very less than the corresponding time of uniform cost search. This shows that a simple heuristic improves the quality of uniform cost search essentially. Is it possible to improve the result? Yes, it is possible. If we define the heuristic based on Manhattan, that means the location of 7 is wrong, but to change the location of 7 to the best location in the goal test, we need to do one step moving down, second step moving down, and third step moving right. 3 steps should be defined. I say that heuristic is 3 for 7. Again for 2. 2 can be replaced by Manhattan distance with one movement to the optimal solution. This is 1. For 5, it is necessary to move one step to right, one step moving again to right. The Manhattan distance is 2. If you use the summation of this value together, you can define a better estimation of the optimal change. Compare with the previous. In the previous, you define for this state h equal to 8, and now you improved it to 18. If you use this better heuristic and implement ASR again with respect to both of the heuristics. In the first version, you consider 13, 39, 227 expanded node, but when you use ASR with Manhattan distance, just you check 12, 25, and 73 expanded nodes for ASR implementation. This simple example shows that it's better to improve the quality of heuristic. For improving the quality of heuristic, we increase the amount of A star by using more powerful heuristic. More powerful heuristic is closer value to the optimal solution. When you need to define the closer value to optimal solution, you need to satisfy more constraint. If you consider more constraint, you can improve the quality of your heuristic. That's enough for this lecture. As a summarization, in this lecture, we improved the quality of A star by using admissible heuristics. Admissible heuristics are some optimistic estimation of the distance between any state to goal state. As much as admissible heuristic closer to real and optimal solution, the performance of ASR improves. In the next lecture, we focus on some mathematical models for relaxed problem, and also we extend our searching space from tree search to graph search. In the graph search, admissible heuristic is not useful. More modern heuristic is needed. We define consistency in that case and define a new version of heuristic that needs to guarantee to find optimal solution in the graph search. For the next session, in the classroom, we can discuss more and we can improve our knowledge about heuristics. Thank you, everyone. I'm ready for your question. If you have any question, I am ready to respond. Is there any problem? Is
You are
this
now
necessary?
unmuted.
Is this necessary to discuss more?
You are now muted.
No need? Thank you. I hope the best of the best for you and your family. See you later. Goodbye.